Have you ever wondered where things like ChatGPT or Bard really came from? Well, you can trace so much of today's AI back to this one single 8-page research paper that a team at Google published back in 2017. And the title was just so simple, almost elegant. Attention is all you need. So let's crack this thing open and really see how it just completely rewrote the rules for artificial intelligence.
To really get why this paper was such a bombshell, you've got to understand the problem everyone was stuck on. I mean, imagine trying to read a long sentence, but you can only see one word at a time. By the time you get to the end, the beginning is already getting kind of fuzzy in your memory, right? Well, that was pretty much the roadblock for older AI models.
All right, so here's our game plan. First, we're going to dig into that old problem with reading things in sequence. Then, we'll get to the wild new idea of attention. After that, we'll peek under the hood to see how these transformer models actually tick, check out their unbelievable results, and finally connect the dots to how this paper became the literal blueprint for the AI we're all using today.
Okay, so first up, let's talk about that wall AI had slammed into before 2017. The problem wasn't a lack of data or slow computers. No, it was something much more fundamental. It was a bottleneck in the very way machines read.
See, the big players back then were these things called recurrent neural networks, or RNNs for short. And as the paper points out, they were inherently sequential. They had to read word by word by word in a straight line. This was a massive bottleneck. Not only was it slow, but it made it super hard for the model to link a word at the end of a paragraph to an idea way back at the beginning. The context just got lost.
Now, this is where it gets really interesting. You can see the whole story right here. On the left, you've got the old way, these recurrent models chugging along one word at a time, slow. And the longer the sentence, the harder it is to connect the dots. But on the right, you have self-attention. It looks at all the words at the exact same time. It's built for parallel processing, so it's way faster. And this is the crucial part. Connecting a word at the beginning to a word at the end is just as easy as connecting two words right next to each other. This was an absolute game changer.
And that brings us to the core genius of this paper. Instead of just trying to patch up the old sequential models, the researchers just threw them out, the whole lot. This wasn't just a small tweak, it was a total reimagining of how machines should understand language, not as a line, but as a web.
And you can just feel the confidence in this sentence from the paper. I mean, this was basically a declaration of war on the old guard. They're saying, we're getting rid of recurrence, and we're getting rid of convolutions, which were the two main tools everyone was using. They were betting the entire farm on this one new idea, attention.
So what is this magic sauce, self-attention? Well, the simple way to think about it is this. It lets the model look at every single word in a sentence, and for each word, figure out how important all the other words are to its meaning. So for a sentence like, the robot picked up the ball because it was heavy, self-attention helps the model figure out that it refers to the ball and not the robot. It just instantly builds this rich map of context.
Okay, so we've got this big idea of self-attention. But how do you build a whole model out of it? Let's take a quick look under the hood of what they called the transformer.
So, from a bird's eye view, the transformer has two main parts. You've got the encoder on the left, and its whole job is to read and really understand the input sentence. Then you've got the decoder on the right, and its job is to spit out the answer, like a translation. But the real secret, the engine driving both of these parts, is that they're just built from stacks and stacks of these self-attention layers.
So how does the attention part actually work? It's a really beautiful process. For every word, the model creates a query. You can think of it like the word asking a question, like, hey, what's my role here? It then takes that query and compares it to a key from every other word to see how relevant they are. Those relevance scores then decide how much weight to give to each word's value. And what comes out the other side is a brand new version of that word, one that's now packed with all this amazing context from the entire sentence.
But of course, they didn't stop there. They figured, why ask just one question at a time? So they came up with multi-head attention. The best way to picture this is to imagine a whole panel of experts, say 8 of them, all reading the same sentence at once. One expert is just focused on the grammar. Another is looking at who did what to whom. A third might be analyzing the poetic meaning. By having all these heads work in parallel, the model gets this incredibly rich 3D understanding of the language. It's brilliant.
Now, there's a really sharp question you might be asking right now. Wait a second. If you look at all the words at once, how does the model know that the dog bit the man is totally different from the man bit the dog? And that's exactly what the authors figured out. They came up with this super clever solution called positional encoding. They basically add a unique mathematical timestamp to each word using sine and cosine waves. This gives every single word a distinct signature based on its position, so the model never loses track of the original order.
So, you've got this beautiful, complex, totally new architecture. It's elegant, it's clever, but the million-dollar question, or maybe billion-dollar question, was, did it actually work?
And the answer was a massive, resounding yes. Just look at these results for machine translation. The score they use is called BLEU. All you need to know is higher is better. So check out that English to German column. The very best models before this, even when you bundled a bunch of them together, maxed out at a score of 26.3. Now, look at the bottom row. The big transformer model hit 28.4. That wasn't just a little better, that was a whole new state-of-the-art.
That leap of over 2 full BLEU points was frankly insane. In that field, researchers would celebrate for weeks to get a 0.1 point gain. To see a jump of 2 points from a single new idea, well, that just doesn't happen. It was a clear signal that everything was about to change.
And here's the kicker. It wasn't just better, it was so much faster to train. The paper mentions their base model trained in just 12 hours on 8 GPUs. I mean, the models it was beating often took days or even weeks to train. So they had achieved the holy grail, a model that was both higher quality and way more efficient.
So yeah, the results were historic back in 2017. But the real story, the reason we're still talking about this paper today, is everything that happened next.
Because the architecture they laid out became the foundation for pretty much all modern AI. Google's BERT model, which totally changed web search, that's the Transformers encoder. OpenAI's GPT series, the engine behind ChatGPT, that's built on the Transformers decoder. Lambda, you name it. Nearly every single large language model making headlines today stands directly on the shoulders of this one paper.
Looking back at it now, the author's conclusion is just a beautiful, classic piece of academic understatement. We are excited about the future of attention-based models. It's incredible. They had to be excited, but they probably had no idea they had just handed the world the blueprint for a full-blown AI revolution that was about to kick off.
In the end, what this paper really shows us is that one single powerful idea, that you can understand language as a web of relationships instead of just a line of words, can change absolutely everything. And it makes you wonder, right? As we sit here in this world that Transformers built, what simple, radical idea is someone writing down in a research paper right now that's going to spark the next AI revolution?